XGBoost, short for Extreme Gradient Boosting, is an algorithm designed for big datasets. Datasets with a large number of features and samples. In this video, we'll look at the details of how this algorithm works using concrete examples. By the end, you'll have an intuitive sense of how it works, how you can tune it and use it for any problem you're solving using machine learning. Welcome to Scovia Labs, where we turn ML ideas into everyday intuition. Let's spend a minute revisiting how machine learning works with data. Data consists of features and labels. If labels are categories, it is called classification. If labels are numbers, it is called regression. We have seen in the past that decision trees can do both. If you're unfamiliar with what a decision tree is, please watch our video. A link is posted in the description of this video as well. XGBoost, which is short for Extreme Gradient Boosting, is a fast, regularized form of gradient boosting using trees. A single small tree is like a rough sketch. Boosting adds another small tree that focuses on the leftover mistakes, which is also called residuals. Then another tree and another, each one nudging predictions in the right direction by a small step. Note that this is different from what algorithms like random forest do, which grow many trees in parallel and then average. Boosting, on the other hand, grows many trees in sequence, each trained on what's still wrong. With this background, let's jump into how XGBoost works. Extreme gradient boosting is a big algorithm with a lot of components to it. There's gradient boosting, there's learning rate, there's tree capacity and stopping, and regularization. We'll go over each of these components one by one using a simple example. Note that the algorithm will look like an overkill for this small example. The idea is to show how it works on a small dataset, which helps imagine how it might work on a bigger one. Let's start with gradient boosting. Consider an example where you're predicting the energy demand of a building based on the temperature outside. And a plot of it looks this way. X-axis is temperature and y-axis is power consumed. Given this data, goal is to build gradient boosting tree. First step in gradient boosting is to calculate the mean of the prediction variable, which is the power consumed in this case. So the mean value is equal to 8.8 here. After this, we calculate something called the residuals. Residuals are the errors in prediction compared to the mean in this case. We calculate another metric called the similarity score, which is sum of all residuals, which are then squared and divided by the number of samples. Note that the positive and negative residuals cancel each other out, since we do not square the residuals before adding them. Having a large value of similarity indicates that most errors are in the same direction and is considered good. The next step is to build the tree. This is a special tree, which is built quite differently compared to a vanilla decision tree. We'll show three candidates, 2.5, 7.5, and 12.5. The recipe is the same each time. So let's start with the threshold 2.5. First, the residuals are sent left or right based on whether they satisfy the condition of x being less than equal to 2.5. Then we compute the leaf value in each child, which is the mean residual in that child. This turns out to be 5.2 for the left child and negative 0.5778 for the right child. After this, we compute each child's sum of squared errors and similarity. Finally, we compute the gain, which is the sum of squared errors of the root node minus 30.04 as well. When we execute this step with different thresholds, we get different gain values in each case. Among these, 7.5 gives the largest gain, so it becomes our root split. We can grow this tree one more level. We can split either of the child nodes. We'll choose the single split that gives the biggest additional gain. Splitting the left child results in two singletons giving a gain value of 4.5, while splitting the right child at a threshold of 37.5 provides a gain of 35.0417. Since 35.04 is greater than 4.5, we split the right child at 37.5. Let's now talk about learning rate in the context of XGBoost trees. To do that, we first need to look at how our tree makes a prediction. Take the tree we just split. We'll call the model's prediction rule to be a function of x. That just means what number the model outputs for an input x. In our case, the function of x is to start with the baseline, where the mean is 8.8, and then send x down the tree to a leaf and read off that leaf's correction, and add that correction to the baseline. For our depth 2 tree, the leaf corrections are shown here, and you can see how it traverses this tree to calculate the final value. This calculation we went over is the no shrinkage version, where each tree's correction is added at full strength. Now, learning rate, which is also called shrinkage, and it's written as eta, is simply something that scales the correction before we add it. Think of it as a volume knob for each tree's contribution. Mathematically, using the same tree but with the shrinkage eta looks like the following. Note that we are essentially shrinking the contribution of every tree in correcting the prediction value. Depending on what the value of eta is, you may get slightly different values. And you see examples of what happens when eta is equal to 0.5 or equal to 0.2. So why do this? So it turns out that a smaller value of learning rate means smaller steps per tree, which is safer and less likely to overfit. You can think of eta as a volume knob on how loudly each tree speaks. Shrinkage doesn't change which split we pick in the current tree. We still choose splits by gain or sum of squared error reduction or similarity gain. Shrinkage is applied after the tree is built, when we add its leaf values to the model. Shrinkage changes the next round's residuals. With a smaller eta, our first tree only partially corrects the errors, so the residuals stay larger and clearer for the next tree to learn from. That's the slow and steady behavior that people like about XGBoost. We now have our first gradient boosting tree, and it uses the baseline 8.8 and 3 leaf corrections. With a learning rate of 0.5, each correction is added at half strength. Gradient boosting always works on the errors left by the current model, so we recompute the residuals after tree 1, and those become the training targets for tree 2. Residuals from the first tree are calculated by predicting the target for each sample by passing them through the first tree and then subtracting it from the true value. We'll follow the same recipe as before to construct our second tree. We test for different thresholds and select the best one for the root node. The difference is that we work on residuals that are calculated from the first tree. While constructing the first tree, we used residuals calculated from the average value. Here, we are using the residuals not from the average but from the first tree. One can construct multiple trees by targeting residuals of the previous tree. Now that we understand gradient boosting and learning rate, let's talk about tree capacity and stopping. There are a few knobs that we can use to control how the tree grows. The first one is setting a limit on either the tree depth or the number of maximum leaves allowed. Smaller trees ensure gentler local corrections. Another knob is the gamma value, which sets a condition that a node should only be split if the gain is big enough. If the gain from splitting is not big enough, the node is not allowed to split and becomes a child node instead. These are metrics to control tree growth, right? Now there's another metric that you could use as an early stopping condition where you could stop adding trees if the validation metric does not show improvement. Next, let's talk about regularization, where it lives in the equation and what it does. Our earlier equation for calculation of similarity looked like this. When regularization is added, the new equation has a lambda value in the denominator. This lambda acts like adding virtual points to every leaf, which makes the similarity shrink. As a result, only the strong, consistent residuals look attractive. Similarly, the sum of squared error value before adding any regularization looked like this. And this calculation after regularization looks like this. The previous equation for gain that we saw looked like this. And now the new equation, once you add regularization and the gamma value, which we talked about before, the new gain would look like this. The gamma value here is like a toll that's added to the gain calculation. You only split if the gain is bigger than gamma. Otherwise, the gain becomes negative and there's no point in splitting the tree further. Idea is that lambda shrinks leaf corrections towards 0 and gamma charges for making a new leaf. Together, they discourage tiny, noisy splits and keep the tree modest. In summary, XGBoost is still gradient boosting. Many small trees that fix what the current model gets wrong. But extreme means it's tuned for power, control, and scale. It uses both the error and its curvature to set leaf values and picks splits so each tree corrects the most important mistakes faster. It bakes in regularization and handles missing or sparse data natively, reducing the overfit. And it's heavily optimized, so it trains much faster on large datasets. So that's a wrap. Thanks for joining us on Scovia. Hit that subscribe button for more eye-opening AI stories and insights. Stay curious and keep exploring.